So today we will study Newton's method. So what it's about? Let's see the motivation. Why we are interested in studying this method. Since we started studying a function, we had to solve equations. Okay, we had to solve equations like fx equals 0, a function, nonlinear function equals 0. This comes with the intersection of the graph of f with the x-axis, for example. Okay, we need to solve the equation f prime x equals 0 to find the critical points. Okay. We needed also to solve f second equals 0, x equals 0, also to find the inflection point. Okay, inflection point. Okay, so each time we had then to solve an equation, but as long if the function is not simple as linear or second-year, we have no control on the existence explicit solution to find an explicit solution. But still we need to know if it exists and where approximately it is located. So Newton's method answers this question. So let's describe the method. So how is the method? It's based on what? Okay. Okay, so suppose that we have to solve an equation fx equal 0, and suppose that we could locate our root, okay, somewhere. Okay. Okay, so suppose that we have a curve, okay, and we would like, and it, let's say, so it crosses the y-axis at somewhere here. Okay, let's graph it well. Let's use nice graph here. Okay. So suppose that okay, so suppose, so we are looking to find this root. Okay, we want to find this point. Where is it to approach it? And let's say we know that it will be like using the intermediate value theorem, that our root is somewhere close to in certain interval, and take an x0 from this interval, and consider then the tangent line at x0 to the curve. Okay, so we have a tangent line. We will let's use this color. So we will graph the line, okay, the tangent line at x0, and this tangent line will cross the x-axis at the second point x1. So the tangent line, let's write its equation. So it has the equation y minus fx0 equal f prime, the slope is f prime x0 times x minus x0. Okay. Okay, then the intersection now, intersection of the line with the x-axis, okay, the line OX. Okay, so the intersection we will obtain it by taking y equals 0, 0 minus fx0 equal f prime x0. So the intersection will be at x1 minus, we called it x1. So if you yes, if you divide by f prime x0, so we and move x0, so we obtain x1 is equal x0 minus f x0 over f prime at x0. Okay, now so we have x1, and the idea is to repeat the process. Okay, consider at x1 the tangent to the curve at x1 and look to the intersection, okay, and call the intersection x2. So let's do it one more time. Tangent line, the tangent line with its equation fx1 minus equal f prime at x1 and x minus x1. Okay, the intersection with OX. So 0 minus fx1 equal f prime at x1 times x2 minus x1. Okay, and similarly we will have x2 equal x1 minus f prime f at x1 over f prime at x1. And imagine we continue like that. Finally we will have a sequence of point xn. Okay, so xn equal, let's say, yes, xn equal the previous xn minus 1 minus f xn minus 1 over f prime at xn minus 1. Okay, so there is yes, and we hope that this sequence approaches the root. Okay, the solution R. Okay, or alpha, let's call it alpha the root. Okay, so of course this is not guessing. There is a theorem. Rigorously we prove that it approaches, and as long as we satisfy the conditions of the theorem, we can prove that this quantity will approach the root, the real root. Okay, here is it, and this approach it. So so under certain certain conditions, certain assumptions. So it's not the purpose of the course. We can prove that xn minus the root is less than x0, the starting point, minus alpha power 2 power n, and times m over 2m, 2 small m, yes, and 2 power n minus 1, where capital M is the maximum of the second derivative, okay, and the small m is the minimum of the first derivative. And we have, of course, we said many other conditions, okay, so that everything will that ensures that we have the convergence. When n is large, when we increase the number of iterations, we are approaching the root. Okay, so one of the conditions you see here, we need that to be sure that we have that the root, the derivative at each step is different from 0. Okay, so yes, we can see it, it's necessary. Okay, so this is how this is the idea of Newton methods. So okay, and you see there is an algorithm. It's something that we can implement. It is implemented in computers, like programs. So you enter just the initial point x0, and then you call your subprogram and compute all the iterated and gives you can ask for specific precision for your error, so that you get an approximate value of xn, okay, within a few steps. Okay, so this is the idea of yes, for example, so this is, yes, we're not, so why it is important. Yes, so many problems can occur. For example, let's look at have a look at this example. Okay, so suppose that you are asked to find the root of fx equal x2 minus 5 equals 0. Okay, so we know in advance that the roots are x equal plus or minus square root of 5. So the method, so it will work as long as you are satisfying. So depending on x0, you are choosing where x0 closest to what. Your solution may converge to square root of 5 and minus square root of 5. So you need to really work and work rigorously. Okay, the choice of x0 is important. those estimations are important and everything. Okay, so this is the kind of problems that may occur. Okay, so for example here f prime of x is 2x, and if you take you start from x equals 0, you have the derivative equals 0, so it will not work. Also the method doesn't work, etc. Yes, so the sequence here will be in like that. So it will be x in the form we said xn equal xn minus 1 minus fxn is xn minus 1 square minus 5 over the derivative 2xn minus 1. Okay, and if you compute here, for example, start with the starting point, start with x0 equal 2 if you want to approach square root of 5. So we will have x1 will be, so x0 minus x0 square minus 5 over 2x0, which gives us 2.25 if you substitute. Okay, x2 second step, it's x1 minus x1 square minus 5 to x1. You will get the value 223611 approximately, and look at x3. If you continue, you will get 223606 977. So usually we stop when we are close to when some numbers are repeating themselves. Okay, for example here the three numbers here are repeating, so we can't stop if we want precision of accuracy of 10 minus 3. Okay, 10 power minus 3. So here is how this is the main idea. Okay, so, yes, keep in mind that it works if you are under the assumptions of the theorem. Okay, so at this level now, practically we first locate in practice now. Okay, so in practice you need to okay, so you need to locate your, okay, in practice, for practice now, in practice for our level here, we need to locate an interval, the root in an interval by the for example intermediate value theorem. The mean value theorem sometimes also works. Okay, then choose once you locate, choose x0 in the interval. Okay, in this interval and then what can you do? Then compute xn. Okay, compute the xn. Okay, and stop. Okay, at m decimals. Okay, xn and stop when you get when xn and, for example, and xm iterated at level m agree at m decimals. Okay, or xn and the following one nn plus 1 agree at m decimals. Okay, so in practical way, think to do that. Okay, so this is the this was the short description of the method. Okay, and it is generalized for for function of several variables, and it works. Yes, it gives us a lot of many solutions. Okay, so let's look at for solve the equation I told you. So yes, using Newton, or call just the subprogram. You see here we are calling the subprogram new Newton method, and here we are asking for sequence. It gives us all the values. Here we ask them to plot, so they plot the tangents and the values, and yes, that's all. Okay, so let's Okay, so let's look at following. Now we started with x0. You see here that I start for -2. So here I approached square root 5, but this time I'm approaching square root minus square root of 5. You see, I get iterated numbers are negative. But now look, when I start at x equals 0, we saw that by calculation the derivative is 0. It stops here. Error. In student calculus, the derivative is 0 after the first iteration. So you have to pay attention to these details. Okay. Okay. So this is what. Yeah. Okay. Thank you.